Okay, part 3. Explain briefly why in is an integer for n equals 0, 1, 2, and so on. All integers greater than 0. Okay, now, what was in? We proved that in was equal to this expression here. And we were also told at the beginning of the question that I of 0 equals, let's see, what was it? It was equal to 2, and I of 1 is equal to 4q squared. Okay, great. Now, let's have a look at I2. That's equal to 4n minus 2. Sorry, 4n minus 2. Well, this is 2 here, so 4 times 2. Q squared, I of 1, minus p squared, q squared, I of 0. So this is 8 minus 2, which is 6, times I1, which is 4q squared. So 6 times 4 is 24. And then q squared times q squared is q to the 4, minus p squared, q squared, times I0, which is 2, so I'll just write the 2 out the front. Okay, so is this an integer? Well, in the question we were told that pi can be written in the form of p and q, where p and q are integers. So if p is an integer, then p squared is an integer, and any integer power of p is an integer. So, p being an integer means that p squared is an integer. And similarly with q being an integer, that means that q squared, my pen's beginning to run out, q squared and q to the 4 are integers. So what do I have? I have an integer in 24 multiplied by q to the 4, which is integer. So integer times integer is integer. And here I have 2 times an integer, so this is an integer. So the whole thing is an integer. I2 is an integer. Good. Now what about I3? Well, I3 is going to be 4 times 3, which is 12, minus 2, which is 10. Q squared, I squared, minus p squared, q squared, I1. Now again, I1 is clearly an integer. It's 4 times an integer. So this expression here is an integer. It's just a product of integers. I2 we said was an integer. Q squared is an integer, 10 is an integer. So this is a product of integers, which itself is an integer. So I have an integer minus an integer. And what do you know? That's an integer. So I've proven, pardon me, I've shown or proven that I3 is an integer. Now I could continue to repeat this process, and that's called, obviously, induction. I can use induction on n to show that in is something, who cares, but it's just an integer. So I can say by induction on n. Now, in saying this, it's kind of like saying, well, you've asked me to prove in is an integer. I've shown you 2 cases, so bang, therefore I'm going to use induction. It's true. Yeah, that's kind of true, and I haven't exactly shown it or proven it, but it doesn't really say to prove it. It says to explain briefly why it would be an integer, and it is only worth 1 mark. So the examiner isn't actually looking for a rigorous proof, which we could do. We could use induction on n, like a formal induction with our steps, base cases, and so on. In fact, it would be strong induction because it's dependent on 2 things. But anyway, we could use induction. But that's not what the examiner is looking for. They're looking for the conceptual understanding, and in fact, they're pretty much just giving you this result in order to use it later on. Okay, so this would suffice to get you the mark for that question. So moving on to part 4. What does part 4 say? It says prove that 0 is less than in is less than p on q times p on 2 to the 2n times 1 on n factorial. Okay, so let's write that down. 0 is less than in is less than p on q times p on 2 to the 2n, 1 on n factorial, where n is greater than or equal to 0. Okay, so I have 2 inequalities here, and they're bounding my in. Alright, now what is in? Let's write it down again. In is q to the 2n on n factorial, the integral from negative pi on 2 to pi on 2 of pi squared on 4 minus x squared raised to the power n cos x dx. Great. So I have in, and it's bounded by two things, like we said. But what is in? In itself is an integral. And that's key here. Because when I'm bounding integrals, it's very often, or very common rather, that when I'm bounding an integral, my bounds come from actually considering what that integral represents. And what does an integral represent? Well, it represents the area under a curve. So here, it would be a good idea if I could consider what the area under this curve is. Now, what else do we know about this integral? If I was looking at this integral for the first time, the first thing that I usually notice is that I have symmetric limits here, symmetric bounds or limits for my integral. Okay, and I know two things. I know that if this is an odd function, if I'm integrating an odd function over symmetric bounds, the whole thing's equal to 0, which would be probably not true since I'm saying that 0 is less than 0 if this was odd. But anyway, if it's even, well then I can kind of simplify my integral just a little bit. So let's try and show that this is even. So let f of x equal pi squared on 4 minus x squared to the n cos x. Showing that it's even would be, considering f of negative x, that's pi squared on 4 minus negative x squared raised to the n cos of negative x. Alright, I have pi squared on 4. This becomes x squared. Now, cos of negative x is cos of x because cos itself is even. Good. So this thing here is f of x. I have f of negative x equals f of x. So what does that mean? That means f of x is even. Good. So if f of x is even, then I can simplify just slightly my integral. I can make this, instead of going from minus pi on 2 to pi on 2, I can make it from 0 to pi on 2 and multiply by 2. So that's going to be twice q2n on n factorial, the integral from 0 to pi on 2. I think I need a new pen. This is running out. Pi squared on 4 minus x squared to the n cos x dx. Good. Now this is going to be easier for me to consider the area because I'm only looking at a smaller section now. Instead of going from minus pi on 2 to pi on 2, I'm going only from 0 to pi on 2. It's just half the domain. Alright, now, if I want to consider an area, I need to consider what the graph looks like. But this is pretty hard to graph. Okay, even for the top students, this will be really not the easiest thing in the world to graph. But that's okay, we don't really need a very exact graph. In fact, all we really need are the values at the beginning and the end. So what do I mean by that? I need to consider what the value when x equals 0 is and the value when x equals pi on 2 is. So f of 0, which is, remember this is f of x, so f of 0 is the value of this thing at 0. That would be pi squared on 4 minus 0 to the power n multiplied by cos of 0. So this is pi squared on 4 to the n. Now cos of 0 is 1, so this is just going to be pi squared on 4 to the n. But I'm going to see, now you'll see why I do this, but I'm going to write this in this way. I'm going to write it as pi to the 2n over 2 to the 2n. And the reason I want to do that is because if I look here in my question, I can see that I have this 2n power popping up. So if I'm able to get it from my working out, that'll be good. Okay, so that's what f of 0 is equal to. That's this limit. Now what about the other limit? F of pi on 2. Well, we've said already that pi on 2 is a root of this polynomial. So this will become 0 and the whole function will be 0. So this whole function is equal to 0. Now let's get a rough graph. So I have f of 0 equals pi to the power 2n on 2 to the power 2n. And I have f of pi on 2, that's a pi on 2, equals 0. So I want a rough graph. Doesn't have to be too accurate, just a rough graph, because I don't really care what the shape of it is. I know that, let's use a felt tip pen rather than a texter. Okay, I'm graphing between 0 and pi on 2, something really rough, x, y. Now, when x is 0, my function has a value, I don't really know exactly what the value is, but it's something up here. It's non-zero, that's a key point, it's non-zero, so it's elevated up. And at pi on 2, which let's say is here, pi on 2, it has a value of 0. Now, what the function looks like in between this doesn't mean anything to me. I don't care about that at all. All I know is that it's going from here to here, and it's going in a smooth and continuous manner. That's important. So I go something, it could look like this, who knows, but I'm just going from here to here, okay? And the area that this function, or this integral, sorry, in was representing is this shaded area here, okay? And I'm going to call this area A1. All right. So A1 is equal to what? Come on, A1 is equal to the integral, this is really dying now, the integral from 0 to pi on 2 of my function f of x, which was pi squared on 4 minus x squared to the n cos x dx. All right. Now, I need to get a bound for this. And what we usually do when we need a bound for an integral is we consider what are known as Riemann sums. So, Riemann sums is something that you would encounter if you took a first-year calculus course, but let's draw this in. So, a Riemann sum is usually just some rectangles. Now, here I only have one rectangle, so it's a Riemann sum, I guess, a singular. But we're going to consider the area shaded in blue and in the opposite direction. So, this entire rectangular area here. Now, I forgot to write down here that this was equal to pi to the 2n over 2 to the 2n. Right, that's the function value at x equals 0. So I can easily work out the area of this rectangle here, right? It's just going to be the height times the base length. So, and also I'm going to call this A2. Right, and A2 represents the entire, I wrote A1, A2, which represents the entire rectangle. Okay, so A2 is equal to what? It's equal to pi to the power 2n divided by 2 to the power 2n multiplied by pi on 2, right? So it's that length times that length. That's nothing too hard. And I can combine this and I'll get pi to the 2n plus 1 divided by 2 to the 2n plus 1. Great. Now, this Riemann sum, I'm going to refer to it as a Riemann sum. This Riemann sum here is clearly larger than the area which the integral represents. So A2 is clearly larger than A1. So clearly, you could even say from the diagram, I have, wow, this pen. A1 is less than A2. And I could also say that clearly A1 is greater than 0, right? This is clearly there's an area, right? I'm starting at something that's non-zero. I'm coming down to 0. I'm never going below the axis. So this integral, this black shaded area, well, that must be, it must be non-zero. So it has to be positive and greater than 0. So therefore I can say 0 is less than A1 is less than A2. Which is to say what? It's saying that 0 is less than the integral from 0 to pi on 2, pi squared on 4 minus x squared to the n cos x dx is less than this expression, pi to the 2n plus 1 divided by 2 to the 2n plus 1. Good. Now, I want to now manipulate this. So you can see that I have, well, hold on, let's see what we wanted to prove. We wanted to prove this thing here, which was 0 is less than in is less than this expression. Now you can see that I have the 0 already here. I almost have in. I'm just off by a factor of q to the 2n on n factorial, almost sort of like that, something like that. I'm just off by a factor here, and here I have an upper bound. So I want to manipulate this, use some algebraic manipulation to get this to equal in. Now remember, in had bounds of negative pi on 2 to pi on 2. So if I multiplied everything in this expression, let's use a different color here. I'm going to multiply everything in this expression by 2. And I'm going to use the reverse of what I used on the previous page, where I went from minus pi on, minus pi on 2 to pi on 2. I'm going to use the reverse and now change this. Well, this is going to stay as 0. I'm going to change this now to the integral from minus pi on 2 to pi on 2. Where before I went from minus pi on 2 to pi on 2 to the value of 0 to pi on 2. Now I'm going in reverse of this integral, n cos x dx. And that should be less than, not less than or equal to, less than. Well, I can cancel one of these powers of 2, and I'll have pi to the 2n plus 1 divided by 2 to the 2n. Okay, I'm almost there now. I just need to multiply by this constant out the front. Because I have this integral, to get in, I have to multiply by that constant out the front. So, I'm going to multiply everything by q to the power 2n on n factorial. So when I multiply this side by that constant, well, it's 0 times a constant, stays 0. When I multiply what's in the middle by that constant, that will then give me exactly the value of in. And when I multiply this thing by it, I have q to the 2n on n factorial multiplied by pi 2n to the power 2n plus 1 over 2 to the power 2n. Okay. And now I'm going to use that expression for pi where we assumed that it was of the form p over q. Right? So I'm going to say that here we're going to just remember that pi is written as p on q because that's what we've assumed in the very beginning of our question. So I have 0 is less than in is less than q to the 2n on n factorial, and then this is going to be p to the power 2n plus 1 on q to the power 2n plus 1. So that's just the pi bit, and then I'm going to multiply that by 1 over 2 to the 2n. Alright, so now I really just have to manipulate this thing to write it in that form. So this is now just an algebraic problem. Okay, q to the 2n divided by q to the 2n plus 1 leaves me with 1q in the denominator, so I have 1 on q. I'm going to write this 1 on n factorial at the end, so don't worry about that. Now p to the power 2n plus 1 is p times p to the power 2n. I am dividing also by 2 to the power 2n, and you'll see why I split that up, because now I'm going to be able to combine these two. And like I said, I'm going to write 1 on n factorial at the end. And so I'm pretty much there now. I have p on q multiplied by, I can use this as one fraction, p on 2 to the power 2n, and 1 over n factorial. And there I have what I wanted to prove. And it's very important now to say that this is for all n equal to 0, 1, 2, and so on. Okay? And you'll see why I'm emphasizing this all in just a second. Alright, the final part. Given that p over q times p on 2 to the 2n times 1 on n factorial is less than 1. So this expression, remember you can see this relationship here. So given that this is less than 1, if n is sufficiently large, deduce that pi is irrational. Okay, so this is the result that we had from part 4. And now we're given that p on q times p on 2 to the 2n, 1 on n factorial, is less than 1 for large enough n. Right? We're told that if I can make n large enough so that this expression becomes less than 1. Okay? So, for large enough n I have this. Now, what can I say? Therefore, there exists some n, some value of n, greater than or equal to 0, such that this expression holds. I'm going to use this. 0 is less than in, is less than this thing, but I'm saying that this is now, for some value of n, in fact, I'm told in the question, for large enough n, this is less than 1. So there's got to be some n where this thing will be now less than 1. So I have p on q times p on 2 to the 2n times 1 on n factorial. And like I just said, this is going to be less than 1 for some value of m. Okay? So in other words, I don't care about this bit here anymore. I only care that I have this bit. 0 is less than in is less than 1. Okay? So if I have 0 is less than in is less than 1, that's good. Let's call this star. But what do I have from part 3? From part 3, I proved that in is an integer. Right? That's the one where we could have used induction. We could have given a rigorous proof to prove that in was an integer, but we didn't. We just said that it was an integer. We explained it. So I've said that from part 3, in is an integer. All right? Let me call this double star. Okay? So here I have statement star, and I have statement double star. One says that in is strictly between 0 and 1. That means it can't be equal to 0 and 1. It's strictly between them. And the other one says that in is an integer. But what kind of nonsense is this? There's no integer between 0 and 1. So clearly I have come up with a contradiction here. So star and double star is a contradiction. I always spell this wrong. Contradiction. Okay, I have a contradiction here. Exclamation point. All right, so I have a contradiction. Now, what does that mean if I have a contradiction? Well, I've done everything right. I've assumed something. I've done everything right. All my maths has been correct. All the logic, all the calculus, everything's been correct. And I've come up with this nonsensical statement. So that means the thing that I've initially assumed, not proven, the thing I initially assumed must be false, because there's no other place in my working where you can tell me I've made a mistake. So if I have a contradiction, therefore my assumption is false. And what was my assumption? Let's have a look. Suppose, in other words, assume that pi can be written in the form of p on q, where p and q are integers. So therefore I can say pi cannot be written in the form of p and q, where p and q are integers. This is not true. Pi can't be written as p on q. So what does it mean if pi can't be written as p on q? Well, therefore, pi is not rational. Pi is not a rational number, because every rational number can be written as in the form of p on q, where p and q are integers, and in fact p and q can't have any common factors. So if pi is not rational, that means that pi is irrational. All right? And I have shown what I need to show. And this is a really marvelous question. I really love this question. It's a great one. And just to give you a feel of how difficult this question is, it is the last question of an exam, and all of these questions at the end, when you go through and do past papers, you'll find that these last questions are really, really tough. I actually had this question as an assignment in an advanced first year integral calculus course at university. So, I mean, we're high school students here doing the Extension 2 course, but a lot of this stuff is taken from university level, and not just standard university level. They're taken from advanced university level courses. Really great questions, but really challenging as well. They're there to separate the really top genius students from the good and average students. All right, so I hope you've enjoyed this. It's a great one, and yeah, thanks for watching.